audible now?
Yeah, I can hear you and see your slides.
Okay.
Okay, whenever you're ready. Thanks.
Yeah, sure. So, hi, I am Shubhayan Sarkar from Center for Theoretical Physics at the Polish Academy of Sciences. So first, I would like to thank the organizers to give me an opportunity to present my work. So, without taking much time, let me begin. So, today I will be presenting one of my recent works, which is on universal notion of classicality based on ontological framework. So, to begin with, let me introduce what I consider the most natural picture in which any physical experiment can be modeled up into. The picture is very simple. A system comes through the input, it undergoes a process, and there is an output. And this is known as the operational picture. So this picture is good to predict different outcomes of given different physical experiments. But however, what it lacks is some deeper understanding of what is going on in this physical experiment. So what I precisely mean is that let us say that I belong to class of the physicists who assume that there is some physical states of reality out there, and even though we cannot assume it, we cannot observe it directly, but it's something is physical or real out there. So such physical states are or the ontic states are denoted by lambda, and any system is actually a collection of these ontic states, and different systems vary depending on some probability distribution which are over these ontic states. So, and this ontic states go through the input, it interacts with the process, and there is a change of the probability distribution over these states, and that's how you see that your system has evolved to some new state. So comparing operational versus ontological picture, what you see is that preparations are denoted by P, and in the operational picture and in the ontological picture, it is denoted by a quantity like this, which is the probability of getting a state lambda given your preparation P. Evolution or dynamics or transformations are known as T in the operational picture, and in the ontological picture, it is given by the probability of getting some ontic state lambda prime given your initial ontic state was lambda and it underwent a transformation T. And outcomes and measurements are in the operational picture are denoted by K and M, and in the ontological picture, it is denoted by a response function, which is the probability of getting outcome K given your measurement M and your ontic state lambda. So at the end of the physical experiment, what you get is a set of statistics, which is denoted here by a quantity like this, which is the probability of K of getting outcome K given the measurement M for a system P which underwent a transformation T. And in the ontological picture, you can write this function using these three quantities, and you sum over all the lambdas. So in quantum theory, this operational probability can be calculated using this trace function, and this U denotes unitary matrices which acts on some Hilbert space. Rho denotes density matrices defined over those Hilbert spaces, and these MKs are some positive operators which act on those Hilbert spaces. So what is a notion of classicality? So given this ontological framework, what we would like is to understand how is quantum theory different than classical theory. So for this, first, what we have to understand is what are the set of constraints which any classical theory must abide given this ontological framework. So better notions of classicality or stronger notions of classicality would capture greater amount of quantumness. So the most famous example of this is Bell's local causality. So there is Alice, there is Bob, there is a preparation device. Alice and Bob are not allowed to communicate among each other. And then you look at the joint correlation statistics, and if you assume that your preparation device is classical, then it should abide a condition like this, which says that all the all the probabilities which are observed by Alice or Bob are defined locally. So now what we know is that quantum theory violates this. So going in a similar line of thought, our work was to find a new notion of classicality which is much stronger than this. So we find a notion of classicality and term is as universal classicality, and it is based on two assumptions. So the first is that pure states are states of reality. What it means is that given two preparations P1 and P2 that generate pure states, the corresponding ontological distributions that these preparations generate do not overlap. Okay. And the second assumption is that measurements just observe the ontic state. So formally defining it, what it means is that for all pure state preparations Pi, which give you the probability of getting outcome K given some measurement M given those Pi's is equal to 1. What it means is that the response function is 1 for all the lambdas which belongs which are generated by these preparations. Okay. So to see that how quantum theory can outperform classical theories, we find an operational task. So the task is very simple. So there is Alice, there is Bob. Alice has a preparation box, and she has like two switches. She can prepare two different preparations, and Bob has a measurement device, and given the preparations, Bob can perform two different measurements on the preparation. So the success probability for this scenario is defined like this, where each of these quantity is, let's say if I take the first quantity, it says that probability of getting outcome 0 given your preparation 0 and your measurement 0. But to see that actually quantum theory can outperform classical theories, what we need is a constraint which we need to impose in this game. So just like in the Bell scenario, to see that quantum theory actually violates the Bell's local causality, we need to assume that the correlations are no signaling. Otherwise, classical theories can also reproduce the same statistics as quantum theory. So for this, the constraint that we need to impose here that Bob chooses rank 1 measurements. So given this constraint and this operational task and the success probability, what we actually find is that for any theory which satisfies the assumptions of no overlap and strong duality, which I showed before, the success probability is actually bounded by 0.75. And interestingly, you need just a pair of qubits and a pair of measurements, which are like a linear combination of Pauli sigma z and sigma x to violate this bound. And what you can achieve is like close to 0.85. So, and then we move on to prove that the notion of universal classicality also implies other known notions of classicality like Bell's local causality, Cochin-Specker non-contextuality, and preparation non-contextuality. So what it means is that any violation of, let's say that Bell's local causality is violated, then for sure we can say that universal classicality is also violated. However, there might be some scenarios where universal classicality is violated, but not Bell's local causality. So what I can say is that we capture a larger amount of quantumness than these previously known notions of classicality. So for the concluding remarks, we first constructed a notion of classicality termed universal classicality based on two very natural assumptions which we can see in classical physics. Then we constructed an operational task which is bounded for any theory which satisfies this assumption of that pure states are states of reality and measurement just observe the ontic states. Third is that universal classicality can be violated by using just a pair of qubits, which makes this scheme much more applicable in practical scenarios. And then the violations of previously known notions of classicality is also a violation of universal classicality, and in the future we would like to see how this scheme can lead to like new cryptographic task, or something which I'm presently working on is to make this scheme device independent in order to certify the states and the measurements, even qubit states and qubit measurements. Okay, so that's it from my side. You can check the full paper, which is on arXiv, and thank you.
Okay, great. Thank you very much, Shubhayan. We can open the floor to questions now. If anyone has a question, they can raise their hand. Okay, David Schmidt.
Hi, thanks for the talk. Can you talk to the definition of universal classicality? And can you explain the relationship with the assumption of psi ontology? Because it looks like assumption 1 here is just psi.
Yes, exactly. So if you have like psi complete models, then they violate this assumption on this second assumption that measurement just observed, but the states are actually real. So psi ontic models they satisfy this first assumption, but they do not satisfy this. And also for remark, psi epistemic models, they violate this first assumption, but they satisfy this second one. So that's why you can actually see a violation even for qubits.
Okay, I see David Schmidt, you've put your hand up again. Did you have a follow-up question?
I meant to lower it. Sorry about that.
Okay, no worries. Just for people who maybe didn't catch the terminology on that question, psi ontology means that you put the wave function in your ontology. It's nothing to do with psi ontology. Okay, Rob Speckens.
Yeah, thanks. And thanks for the talk. So my question is that first assumption, that's part of your notion of universal classicality, which is essentially an assumption that psi is ontic. You know, it might be complete, it might be psi incomplete, but it's ontic. Why do you think of that as a notion of classicality? Because I mean, the argument that I've made many times is that if we allow psi epistemic models, much more of the quantum phenomenology can be explained in a classical-like theory. So my toy theory, for example, I would consider to be a very classical-like theory. So I'm just curious, why you're calling this a notion of classicality. So
what I would say is here that in classical physics, so if we observe a state in classical physics, so I would expect that let's say I'm talking about Hamiltonian dynamics, for example. So there any state which is defined using the position and the momentum, and I know that my position and momentum is like a physical state. So that's why I say that if it's a pure state, then I take it that the state is actually a state of reality. However, in quantum theory, it can be violated. So like psi epistemic models, so this assumption can be violated for sure. But yeah, so this would be my answer for this.
Is there time for a short follow-up, or?
Sure.
Yeah, we're doing fine for time, so you can, yeah.
Oh, okay. So I think I understood your answer, and I guess I would just say that, purity means extremal in the convex set of states.
Yes.
But if you allow that there could be a restriction on what we can know, so that our most refined knowledge is still incomplete knowledge about the ontic state, then the convexly extremal states of knowledge might still, be not point distributions on the ontic state space. They could be spread out on the ontic state space. So that's why it seems to me that just looking at the pure quantum states and saying, let's make them ontic, that is basically saying it cannot be that the underlying model, has an epistemic restriction and forbids us from knowing the ontic state. Sure.
I completely agree with it. Yeah, sure.
Okay,
so yeah,
thanks.
maybe we can weaken this assumption further. Sure. Yeah.
Okay, I think
Thanks for the comment.
that's a good point maybe to go to break. but we can keep. I'll emphasize that we've got this. We've got a breakout room, or I'll recreate the breakout room now. So if anyone would like to keep on discussing this, and I certainly would, then yeah, we can join this breakout room, and otherwise the next talk will start at 10 past. So thanks again for all the speakers from the last session.